Hello friends, in this lecture we will discuss dark field microscopy and ultraviolet microscopy in detail today. Let us first discuss dark field microscopy. Dark field microscopy is a method which creates a contrast between the object and the surrounding field. As the name implies, the background is dark and the object is bright. Instead of being transmitted through the specimen, the light is reflected by the object on the slide. Hence, the object is brightly illuminated against a dark background. The principle of dark field is simple. Rather than illuminating the sample with a filled cone of light, the condenser is designed to form a hollow cone of light. This is achieved by obstructing the entry of all central rays of light into the objective. There are several pieces of equipment that are utilized to produce dark field illumination. The simplest is a spider stop placed just under the bottom lens of the substage condenser. Both the aperture and field diaphragms are opened wide to pass oblique rays. All peripheral rays are reflected obliquely to the center of the slide when a strong light source is used. The oblique rays do not enter the objective. The entire field appears dark when there is no sample on the microscope stage, thus the name dark field microscopy. We just saw that when there is no specimen on the stage, the microscopic field is completely dark. What happens when we place a specimen on the stage? When a sample is on the stage, the oblique rays will be scattered by reflection and refraction. The image is made only by those rays scattered by the sample and captured in the objective lens. The image appears bright against the dark background. This situation can be compared to the glittery appearance of dust particles in a dark room illuminated by strong shafts of light coming in through a side window. The dust particles are very small but are easily seen when they scatter the light rays. This is the working principle of dark field microscopy. Dark field objects are quite spectacular to see, and objects of very low contrast in bright field shine brilliantly in dark field. Such illumination is best for revealing outlines, edges and boundaries. Three types of condensers are used for dark field illumination, mainly Abbe condenser, paraboloid condenser and cardioid condenser. The Abbe condenser is more commonly used than the other two. The top lens of a simple Abbe dark field condenser is spherically concave, allowing light rays emerging from the surface to form an inverted hollow cone of light with an apex centered in the specimen plane. If no specimen is present and the numerical aperture of the condenser is greater than that of the objective, the oblique rays cross and all such rays will miss entering the objective because of their obliquity. The field of view will appear dark. The cardioid condenser is a high numerical aperture arrangement that represents dark field microscopy in its most sophisticated configuration. The objective contains an internal iris diaphragm that serves to reduce the numerical aperture of the objective to a value below that of the inverted hollow cone emitted by the condenser. The cardioid condenser is a reflecting dark field design that relies on internal mirrors to project an aberration-free cone of light onto the specimen plane. The most widely used dark field condenser is the paraboloid, consisting of a solid piece of glass ground very accurately into the shape of a paraboloid as shown in the figure. Light incident upon the reflecting surface of a paraboloid condenser will be focused at the focal point of the reflector. The light stop at the bottom of the glass condenser serves to block central rays from reaching the specimen. Light rays that are reflected by the condenser are angled higher than the critical angle of reflection and converge at the principal focus of the condenser. The combination of a glass slide, mounting medium and immersion oil complete the optical homogeneity of the paraboloid shape. It is also possible to convert a bright field microscope into a dark field microscope by the addition of a simple stop. The stop is a piece of opaque material placed below the substage condenser. It blocks out the center of the beam of light coming from the base of the microscope and forms the hollow cone of light needed for dark field illumination. This device works fairly well even with the Abbe condenser with the 10x objective up to 40x or higher objectives having a numerical aperture no higher than 0.65. The diameter of the opaque stop should be approximately 16 to 18 millimeters for a 10x objective and approximately 20 to 24 millimeters for a 40x objective. In the operation of the dark field microscope, the best viewing result requires increasing the light intensity as much as possible by setting the light intensity adjustment at maximum, by opening the field diaphragm, by opening the condenser aperture, and by removing any color or other filters. Let us now discuss the applications of dark field microscopy. Dark field microscopy can be used for initial examination of suspensions of cells such as yeast, bacteria, small protists, or cell and tissue fractions including cheek epithelial cells, chloroplasts, mitochondria, and even blood cells. It is also mainly used for the determination of motility in cultures. Dark field examination is particularly useful in the detection of spirochetes like Treponema pallidum in the early diagnosis of syphilis. Spirochetes cannot be seen by light microscopy because of their very thin dimensions. Dark field microscopy is also used for observation of internal structure in large eukaryotic microorganisms such as algae or yeasts. Let us now discuss the advantages of dark field microscope. A dark field microscope is ideal for viewing objects that are unstained, transparent, and absorb little or no light. Resolution by dark field microscopy is somewhat better than bright field microscopy. Dark field microscopy improves image contrast without the use of stain and thus do not kill cells. It enables direct detection of non-culturable bacteria present in patient samples. For dark field microscopy, no sample preparation is required. This microscopy requires no special setup. Even a light microscope can be converted into a dark field. Recently, dark field microscopy has regained some of its popularity when combined with other illumination techniques such as fluorescence, which widens its possible employment in certain fields. Let us now discuss the disadvantages or limitations of dark field microscopy. Dark field images are prone to degradation, distortion, and inaccuracies. Sample material needs to be spread thinly. Dense preparation can grossly affect the contrast and accuracy of the dark field's image and lead to artifacts. Preparation and quality of slides can grossly affect contrast and accuracy of images. The advantage of dark field microscopy also becomes its biggest disadvantage. Not only the specimen, but dust and other particles scatter the light and appear bright. More care is therefore required in sample preparation. Glass slides need to be thoroughly cleaned of extraneous dust and dirt. It may be necessary to filter sample media to exclude contaminants. While using oil on slide, it is impossible to avoid air bubbles. These bubbles cause distortion of images. Color is lacking or minimal, and this can be quite disappointing to the viewer. The actual size of specimens is also impacted, with the width of objects becoming exaggerated. Therefore, this method is not reliable for measurement of specimens. Dark field microscopy needs immense amount of light, which can cause glare and distortion. Let us now discuss the next type of microscopy, the ultraviolet microscopy. Ultraviolet microscopy was developed in 1904 by the German scientists August Kohlherr and Moritz von Rohr. They used UV light as source of illumination generated through a cadmium arc. Because of the shorter wavelength of UV light, higher resolution of up to 0.15 micrometer was possible. Do you remember the limit of resolution of light microscopy? Yes, it was 0.21 micrometer. UV microscopy lenses are made of quartz. This is because the conventional glass lenses are opaque too and also absorb UV light. The image is impressed on photographic film or captured by phototube and projected on screen. Viewing directly at UV light can be harmful to eyes. The UV microscope is a microscope that can image in the ultraviolet region. UV microscopes see beyond what a standard optical microscope can image. With special UV optics, light sources and cameras, UV microscopes image microscopic samples in the visible and ultraviolet regions. This means that UV microscopes have features that make them superior to bright field microscopes. Some materials are invisible in normal microscopes but can be imaged with UV microscopes. One such example is imaging protein crystals. These microscopic crystals are transparent in the visible range but can be easily detected at 280 nanometers due to the strong absorbance of aromatic amino acids. These are protein crystals as seen by bright field microscopy, and these are protein crystals as seen by UV microscopy. Interest in UV microscopy led to the recognition that the electron beam could also be used as an illuminant of very short wavelength, and it was this that gave rise to the interest in the electron microscope. The UV microscope is designed to image in regions beyond the visible range. As such, there are many applications of UV microscopes as they can non-destructively image microscopic samples in regions other than visible. The applications in the field of pharmaceutical and biological sciences are locating protein crystals, pharmaceutical quality control, active ingredient dispersal imaging, contaminant analysis, and cellular imaging. The applications in the field of semiconductors and displays are locating microscopic contaminants on devices, ultra high resolution imaging, materials research. The applications in the field of geology are mineral imaging, petroleum analysis.